Very first question says, hey, look, here's a ball resting here. When you see at rest, you should think of it like, there's no resultant force. Hey, don't scan yet, don't scan yet. Later, I will put a assignment thing for you to scan. After. We mark together, ma. You mark already, you write correction, whatever you want to add, then only you scan. So don't scan now, don't scan now. After. So you see this thing is at rest. That should tell you like, wait, that means there's no net force. Nobody push you, why then you wouldn't move lah. You sit there and chill. So calculate the magnitude of the normal contact force acting on the ball. So normal contact means whenever you touch, you see these two in contact. So got force, contact force. So what's helpful is to draw what we call a free body diagram. What does that mean? Means you ask yourself, okay, here's the ball. What are the forces acting on this ball? There is going to be normal contact force. Okay, yes. What's the other one that pull things down? Assume we are on planet Earth. There is a weight of this object. But why don't the thing drop down? Because somebody stopped it. Who stopped it? The floor said, hey, excuse me, don't go down. Halt! Let me push you up. So there is a normal contact force also acting on the ball. So I draw here. Then now you see, okay, we don't know N. They want us to find N. Nani? Do we know W? Oh, yes, we do know W because we got weight. And weight is the mass times the constant G. So we can say that, all right, since this whole thing is at rest, right? See, at rest now. So I can say that the normal contact force upwards equals to the mg pointing downwards. What points up equal point down. It is up. This is down. So mg will be 0.15 in kg. And g is 9.81. This one, your normal contact force should be about 1.47 Newton. So you could write 1.47. Or if you write 1.5, also okay. Ding. This is 1 mark for final only. Okay, so remember, object is just chilling means no resultant force. You just chill there. So all the forces must cancel out and equal to each other. Okay, so now we have got the working. They ask us to explain. Why did we equate N equals to mg? How to explain? Well, we can say this. Since we already say since the net force or resultant force is 0, because the thing is at rest, it didn't start moving, it's just chilling. Since the resultant force is 0, the normal contact force upwards equals to what? Equals to weight downwards. So opposite direction, 1 point up, 1 point down. Hence, you make them equal to each other. So you got this idea somewhere. Normal contact force upwards equals to weight down. Resultant force 0. Okay lah, can also. Okay, so this is the basic of explaining what is equilibrium. You stay chill, no moving. If nobody push you, you don't move. Then we go to part 2. The ball is now lifted. You take it up and you drop. So it falls. So you see on the left side, this ball here, drop down to the floor. But then, what happens? Just before contact with the floor, the ball has velocity downwards. So this is a V. Oh yo, this is also too big. This is initial velocity. Let's call this. Then the ball bounced from the floor. It hit the floor. Boom, boom. Something happened. Ping, pong, boom. Got sound come out. And just after losing contact is 2.5 upwards. So this is the final velocity. The ball is in contact with the floor for 12 seconds. This is called, I guess, a delta T. Okay, so you have a floor here. Boom, 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 boom. They are in contact for 0.12 seconds. Okay. I think we got a nice setup here. What are they asking? State Newton's second law of motion. Oh, this one. Miss, F equals to ma. Wait, this is not the original. The original is net force is the rate of change of momentum. dp dt or delta p delta t. This one also can. You can also say proportional to rate of change of momentum. This one must memorize. So you can say resultant force. The resultant, if you don't say, is okay. Resultant force is proportional, or you can say equal to what? Rate of change of momentum. This thing, or this thing. The rate of change of momentum. This one only correct. Must say the whole thing. If you write F equals ma, not the OG, cannot. So part 2. Now we have a collision. Ball hit the floor, bounce up. Calculate the average resultant force on the ball when it is in contact with the floor. When it is in contact with the floor. Think about that. Oh, we have a question about the first one. Can say change in momentum over per unit time. Can lah. That one is not as good as this answer, but I can accept. Some past here, they are a bit picky. They won't accept. Okay, never mind. So that's that. All right. Average force when it's in contact with the floor. Okay, how do we draw this? What is happening here? There, you see, there is 12 seconds where is explosion happen. No, not 12 seconds. Sorry, 0.12 seconds when they are in contact, right? So when they are in contact, there's contact force. So it's kind of like this situation now. But let's draw it up. Okay, when the ball is in contact, how do we know what's the resultant force in contact? So you have weight of the ball trying to pull it down, yeah. But there's some other force from the wall trying to push the ball up. This one's going to be much bigger, I suppose. Voila! Push it up. This is the normal contact force. When it is contact. So there are two ways to do this. The first one is to use Newton's second law that we just wrote up there. This one. Net force is change in momentum over change in time. Okay, this one is one way to do this. But what is the change in momentum? We got the force. We're going to find that. But what is momentum? How to find change in momentum? You have to go and look at the diagram again. Oh, one moment is going down. After that, it's going up. Got change in momentum from the change in velocity. So we can do this. We can say change in momentum. Okay, we find that first. Change in P. Delta P, we say final minus initial. Change ma. What's momentum? Mass times velocity. Okay, so this will equal to mass of the ball times final velocity minus mass of the ball times initial velocity. Can this one? Okay, I think the mass is the same. We can factorize out. Yeah. Final minus initial velocity. I just put inside here lah. So now we have to look at the diagram already. Okay, down there. Final velocity 2.5 minus initial velocity 6.2. I just minus like that. Wait. Oh, this is vectors. You have to choose a direction. So if I say upwards is positive, whatever is moving downwards have to be negative. This one you define one. The sign reverse also okay. So if my 2.5 here is positive, then my 6.2 here have to be negative already. Different direction, different sign. So I have to 2.5 minus negative 6.2. So it's actually adding together. Yeah. So the mass will be 0.15 kg times 2.5 plus 6.2. So if you forgot the sign there, write a quick note to yourself. Hey, careful kinematics, velocity, all these got sign one. You choose where positive, where negative. If up positive, down negative. Or the other way around. Okay, change in momentum has happened. Okay, now we can calculate and press calculator. So 0.15 times that should be 1.305. What's happening? Okay. So this change in momentum is 1.305. But that's not the answer, not the force yet. Okay, now we can plug into the Newton's second law. So this average force in this time of 0.12 seconds, it's going to be 1.305 divided by how long they are in contact, 0.12. You can do all this in one step. I'm just writing the extended version of this. This will give you about 10.875 Newton. So this one you can write 11 Newton also can. Direction of force. How do you know where? You can usually say upwards. The net force is upwards. How do we know? Well, you think about this. At first the ball is going down. Then something happened. Ping pong 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 pong. Suddenly the ball is going up already. So why would the object suddenly change direction? Because some force have to push it up. Say hello, don't go down anymore. Go up, boom, give it a punch. That's the flaw. So down here, when it's in contact, there is actually a net force. A weight plus contact force, everybody add together. This one says, boom, go up please. This is the net force. That's why now you change direction already. At first you're going down, now you're going up. Okay? Somebody throw a basketball at you, you smack it away. Boom! The ball change direction. Somebody throw their phone at you. Boom! You push, the phone change direction. Give it a smack. So force upwards, because change in momentum is that way. Okay, so this is 3 marks. This one, if you find the momentum, change in momentum, where's the step? You plug in the correct values. Substitute. This one is the first. P equals mv, but for both. Then you sub in to get 11, this one, or 10.875, this is the next one. And if you say upwards, there is also 1 mark there. Okay, this one can find. There is another method which some of you may have used. You say, Miss, I can find the average acceleration. Acceleration is change in velocity over change in time. Change in velocity, one go down, right? One go up. That can be 2.5 minus 6.2 divided by 0.12, and you get your acceleration, which is about 72.5 meter per second square. Then once you find acceleration, you can say, oh, then I can do F equals to m times a. This one can. So 0.15 times the average. This is average. This is average. This one will be 72.5, and you will also get the same thing, 11. I mean, these both methods are related in this case, so whichever method you use also, you get the same answer. Okay, what questions do you all have about this calculation first so far? None so far. All right. Let's see. Why negative? Why 2 minus? Good question. What is happening here? Final, initial. Okay, let's write down the graph. The graph. Let's write down the values first in this diagram here. So when the ball at first is going down, right? Initial is going down at a speed of 6.2 meters per second downwards. Then after it hit the floor already, it's going up. We call this final velocity. And this is 2.5. But velocity is direction, one go down, one go up. They have to be different signs. So which one do you want to be negative? Since we're doing final minus initial, okay, why this minus? This minus is because we're finding the change in momentum. Final minus initial. So final velocity minus initial velocity. So then we say, okay, if final is going to be positive, then the other one moving down have to be negative. Because they're in opposite directions. So I guess you could put in bracket like this. 25, which is final, minus the initial. Initial is negative 6.2. Hope that clarifies the question. So whenever there's momentum and velocities, be careful with the signs. I will draw a big sticker note and say, hey, be careful with the signs. Okay, the last one. This one have to tell story again. Ayoma. Big story. What's the story? Explain or state and explain whether linear momentum, or state and explain whether linear momentum is conserved during the collision of the ball with the floor. Momentum conserved during collision. Well, how do we know? We could say something like this. So what is linear momentum? Linear means in a straight line, no? Linear in a straight line. Non-linear means what? Means got 2D one. Those type of snooker ball, one come here, one come here, ping pong pong. Suddenly they go like that and like that. This one is not linear already lah. So when we say linear momentum, it means in a straight line. Either horizontal or vertical. So is it conserved? We can say, how do you know if it's conserved or not? Momentum is like this, right? Change in momentum goes to initial, equals to change in momentum final. But where did this equation come from in the first place? Actually, Newton's third law. The force on the ball equals to the force on the floor. Equal and opposite directions. And from this equation, then we can say that the change in momentum of the ball is equal and opposite to the change in momentum of the floor. So actually the floor will move a bit. I mean the whole earth will move a bit lah. But we don't see that happening because the floor is so big. Even if you punch the floor also, you won't really see much difference. But there is a change in momentum. Ball got changed, floor also got changed. So we need to talk about this thing. So here's what I can say. The change in momentum of the floor, which is what I write on the side as delta P floor, is equal and opposite to the change in momentum of the ball. Momentum of ball. So momentum is conserved. Momentum is conserved. Okay. So this is basically saying the momentum idea. The first one you can talk about is if you mention, let's see what's the mark scheme. If you talk about the floor got change in momentum, actually got one. This is 1 mark. And if you say, oh, so this amount, change in momentum of the floor, is equal and opposite to change in momentum of the ball, this one is the other one. So that's this one, they got many different ways to say lah. Ours is most similar to the first one. Talking about change in momentum of wall, sorry. Change in momentum of ball equals to change in momentum of the floor. Other ways you could possibly write is total change in momentum is 0, momentum is conserved. Means the momentum is conserved in this whole system. Ball and floor, total momentum 0. That's one method. The third one is kind of similar to the first. Total momentum of the ball and floor is equal to total momentum of the ball after. This one is your favorite equation. Uh, Total momentum initial equals to total momentum final, which is also total momentum final. So you say, oh, miss, at first got M1U1 plus M2U2 equals to M1V1 plus M2V2. That is this third statement. So many different way to talk about this thing lah. Change of total momentum 0. Momentum is conserved. One question is, if I just say yes, put yes without explanation, does it count as momentum is conserved? They didn't exactly give a mark for yes leh. It's kind of linked, so momentum is conserved. But I think you could get it for the second one. Yeah, you could get it for the first one, no, cannot. But second one, yes. So momentum is conserved. But then this is the M1A1 leh. Means you must say the M only you can get the yes. They're all linked together. Oh no, means cannot. Yeah. So although this 1 mark point, whenever you see a M1A1, this one I want to smack the thing because you have to get the M in order to get the A. So if you say yes, but you didn't say why, then sadly cannot. Sadness. Although it's correct lah. Yes. Here is the yes, equivalent of yes. Momentum is conserved. Yes. Okay, so now your 3 ways to think about momentum. First one, in terms of Newton's third law. Force 1 equals to negative force 2. Or total momentum 0. Or your favorite one, initial equals to final. M1, U1, all this blah 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 blah.